Hello, everyone. Today, I'll present our work at the XR Research Center, Sejong University, on a novel AR object placement pipeline. Our goal was to bridge the gap between fully automated systems, which often ignore user intent, and manual placement, which is precise but labor-intensive. Before diving in, let's consider why placing virtual objects accurately is so important. In AR, even slight misalignment shatters immersion and can derail user tasks, from assembling furniture guided by overlays to training simulations. When objects float or intersect real surfaces, users lose trust and engagement. Whether you're designing an AR game or a complex industrial workflow, getting placement right is foundational. Existing research has explored many manual techniques, such as world in miniature for distant objects. On the automated side, systems like Octo Plus use vision language models to find natural spots, but they don't take real-time relational commands. Our work differentiates itself by focusing specifically on parsing and executing source-object edge triplets in a modern XR context. Object placement is a cornerstone of AR, yet we face a persistent trade-off. Automated systems are fast, but lack user agency. They might put an object in a plausible spot that isn't where you want it. Manual placement gives you control, but it involves tedious nudging and can lead to arm fatigue. We wanted to enable a system that understands specific spatial relationships like behind or on the right of. We start by capturing the user's voice and a frame of their environment. We then extract a triplet: the source, or virtual object, the object, or physical reference, and the edge, which is the spatial relationship. This is processed alongside real-world depth and segmentation data to compute the optimal 3D coordinates in Unity. Standard name entity recognition models, including zero-shot Galena, were insufficient for reliably extracting our specific source-object edge triplet structure, particularly the spatial relations, edge. Therefore, we curated a custom dataset comprising 930 samples annotated with these triplets. We fine-tuned Galena, which achieved a 98% F1 score. For scene understanding, we found that grounding Dino provided much more accurate bounding boxes for indoor objects than AWL VT. Similarly, we selected Depth Anything for its superior precision in complex indoor environments compared to traditional transformers. To ensure virtual objects are placed in feasible, empty locations, the system identifies potential spawn areas. We utilize the segment Anything model for this task. SAM segments all distinct objects/surfaces in the image. We filter these segments based on a minimum area threshold to focus on significant surfaces. OpenCV is then used to extract the polygonal vertices defining the boundaries of these segmented areas, particularly identifying empty or flat surfaces suitable for placement. This step identifies candidate regions where virtual objects can be placed without intersecting existing physical objects. Once we have the data, we use a cost function optimization to find the final position. This function balances four factors: how well it satisfies the requested spatial relationship, avoiding overlap with physical furniture, maintaining depth consistency, and ensuring the object is scaled correctly for the surface it's sitting on. We evaluated this against a manual placement control group in a study with 50 participants. We designed 5 tasks that tested various spatial dimensions: vertical occlusion, horizontal precision, and perspective-dependent relations like in front of. The results were highly significant. Our pipeline was over 53 seconds faster per task than manual placement. Remarkably, it also improved placement accuracy, providing more consistent results. In our interviews, we discovered a trade-off between realism and cognitive load. Manual, direct manipulation feels more immersive and real to some, but the mental effort required to get it right is high. Our system frees the user to focus on their creative goal rather than the physics of placement. The most common request was for a hybrid system: automate the initial drop, Then let me fine-tune it. We did observe some limitations. Our pipeline occasionally struggled with sizing objects in occluded spaces, like under a table. Also, depth estimation models still don't quite match human perception for small objects on trays. Finally, the field still lacks a standardized benchmark, which makes comparing different placement methods difficult. To conclude, our pipeline demonstrates that intent-based automation is a practical path forward for AR. We achieved faster completion times and higher satisfaction while maintaining high accuracy. In the future, we plan to implement a hybrid model that allows for manual fine-tuning and explore its use in high-stakes fields like surgery or maintenance. Thank you.